So the overview here, Ben, is you make your matrix.
Yeah.
Okay, from the coefficients of these numbers.
Yeah.
Okay, 5 minus 1, 3, 1. Then you go down and you take the matrix minus lambda times the identity matrix equals 0. Now, there's a shortcut so you don't have to be working with these matrices, although they're fairly simple. All you have to do is subtract the lambda from the diagonal matrix. Okay?
Right.
And then leave the other entries the same. Take the determinant of this and set it equals 0. That's your characteristic equation. Okay? And then from here on, the determinant is 5 minus lambda times 1 minus lambda minus 3 times minus 1 equals 0. Set this equals 0. Solve for your lambda. You get 2 lambdas. One is 4 and one is 2. There's 2 eigenvalues. Oh, by the way, so if the lambdas are positive and real, what does that tell you about the stability of the points? The real part is greater than 0, yeah?
Yeah.
Then the equilibrium point is what? Unstable.
That's unstable.
So therefore, equilibrium we can add here. Equilibrium unstable. Because the real part of the eigenvalue turned out to be greater than 0, and there's no complex part. Okay, so we're just looking at the real part of the eigenvalue. No?
Yeah, that means the x part of the x derivative is and the y
Right.
part of the y derivative is positive.
Right. Then you take your first eigenvalue, you plug it back into this matrix here.
Yeah.
Okay. So you get 3 minus 1, 3 minus 1. You multiply it by an unknown eigenvector that you're trying to find, and you set this equal the 0 matrix. And then you get 2 equations, which are linearly dependent. So there's no point writing both. If you write one, it'll be the same. So that equation is 3a minus b equals 0. Notice that the second one will give you the same thing. So now you assign a value for a or b. So you say if a is 1, plug it in, you get b equals 3, which means 1, 3 is your eigenvector for the first eigenvalue, lambda equals 2. Then you do the same exact process with the second eigenvalue, lambda equals 4. You plug it in here. You plug it in this. Okay? And then you get 3 minus 1, down here. You get 1 minus 1, 3 minus 3, and then you multiply it by the unknown eigenvector, and you set it equal to the 0 matrix. And again, you get 2 linearly dependent equations. You take one of them, c minus d equals 0. You assign a value of c, so if c is 1, d is 1. So that means your second eigenvector is 1, 1 for the second eigenvalue, lambda equals 4. And that enables you to write the solution in this form. xy equals, the lambdas are the exponentials, are the exponents on the exponential term. Okay, so e to the 2t multiplied by its corresponding eigenvector, which turned out to be 1, 3, times some constant c1, plus e to the 4t, because the second eigenvalue is 4, times its corresponding eigenvector, which is 1, 1, times c2. You can equally write this as 2 separate equations. One is the x equals c1 times the top part. It's just matrix multiplication. c1 times 1 times e to the 2t plus c2 times 1 times e to the 4t. And then you could do the same exact thing with the y. So you could say y equals c1 times 3 times e to the 2t plus c2 times 1 times e to the 4t. And you get the second equation. So this system of equations is the solution for your two differential equation system. All right. Questions on that?
All right, I see. So those are the two lengths. coefficients of t.
You mean the 4 and the 2? Those are the eigenvalues, and 1, 3, and 1, 1 are the eigenvectors.
Okay. All right. Well, you said that if lambda is positive and real, that means that it's
the equilibrium point is unstable.
What if I got one that's positive and real? It's not. Does that mean it's a saddle?
If you got one that is greater than 0 and one is less than 0,
Does that mean it's a saddle?
yes.
Yeah.
Then the equilibrium point is a saddle.
One
yes.
dimensionally unstable.
Got it?